Thank you very much. Can you hear me or?
Yeah, we still cannot hear you.
Can you hear me now?
Yes.
Did you say yes?
Yes, yes.
Okay, very good. This today I will use slides rather than handwritten stuff, and which means I will go less into sort of details and proof and more sort of an overview. However, I will start with a couple of minutes sort of roundup from last lecture. So for that reason, I will start by going back to my handwritten stuff. So now I will try to share screen with my iPad. Let's hope that works. So can you see my handwritten stuff? This was this whole thing was from last time up until the last thing I wrote on Tuesday was this. One thing I would like to add was that all the results I talked about on Tuesday, none of them were my results. So it was just sort of results from others and quite a lot of folklore, and I wouldn't know who was the first approving each of those results. However, I have written 2 research monographs, or maybe even 3 research monographs, and you can find the results with more details in 2 of these books. Well, actually in the 3rd one, I wrote one a couple of years ago as well, but maybe the first 2 are better. So one was published over 20 years ago with a Swedish colleague, and then 9 years ago with 2 Dutch colleagues, Odo Diekman and Hans Hesterbeck. So if you want to learn more about details in the proofs, you can go to those 2 books.
I think at least one of them we have here in our library upstairs.
Unfortunately, it was lagging. Can you repeat the question?
I just said we actually ordered one of your books and it's upstairs for people to look at.
Okay, very good. So I'm at my summer cottage. I'm at my summer cottage, and I'm afraid that my connection is not as good as last time. So let me know if I'm lagging or something. Anyway, I didn't say all that much explicitly about the final size for the standard epidemic model that I talked about. Can you turn, now I got to comment, can you turn your iPad sideways? Yes, sorry for that. There we go. I will say a few more words about this thing. The probability of a minor outbreak we call that thing pi, and an expression for getting infected in case of a major outbreak. Okay, and hopefully you remember that the initial, so I would say a few words about this pi, the probability of a minor outbreak, and an expression for the final fraction getting infected in terms of the model parameters. The initial phase, I hope you maybe remember this, of the epidemic was well approximated by a branching process. And what about the offspring distribution? I didn't say this explicitly. So you could sort of think of the model. If this is the index case, maybe if you remember, you were infectious for a period. And during this period, you infected each other individual at some rate beta over n, and you did so for a random infectious period time. And so maybe it looks like this, that here you have the index case, you are infectious for a random period of time, and maybe the outcome is that you infect 3 people. And then maybe you recover. And then these 3 people, they will have sort of the same outcome. So they will also infect according during their infectious period at the same rate. Maybe this one didn't infect anyone, this one infected 2, and this one infected 3. So what is the distribution of how many people you infect? Well, if you first condition on the duration of the infectious period, then you infect a binomial number. And what is the probability to infect a given other individual? Well, it is 1 minus the probability not to infect the other individual. And that thing was beta over n times this iota, which was the length of the infectious period. And this is, of course, approximated by a Poisson distribution, and it will be beta times iota. This means that unconditionally, you infect, then it's no longer independence. So if you have a long infectious period, you're more likely to infect each of the other individuals. So the infection will, whether you infect 2 different individuals, they will be dependent if you have a random infectious period. But anyway, it will be mixed Poisson with beta times this random variable, which is the infectious period. And for the 2 special cases that I talked about earlier, the Reed-Frost model, where we assume that the infectious period was not random, it was equal to 1, let's say, then you infect, then it's no longer mixed Poisson, it is times beta, or in that case, beta is equal to R0, so it will be Poisson R0. In the Markovian case, then if you remember, I said that it was either exponential 1 or exponential gamma. Then it is possible to show that you have the mixed Poisson will then become geometric with parameter gamma divided by gamma plus beta, and that in terms of R0, that will be geometric 1 over 1 plus R0. And if you know the offspring distribution in a branching process, you compute pi. So that's the probability that the branching process goes extinct, but I rather prefer to call it that you have a minor outbreak. If you remember how to do that, you sort of condition on how many are born in the first generation. So you condition on, let's call this thing Z, this random variable Z. And if K individuals are born in the first generation, then of course all of these K offspring, their resulting branching process, all must go extinct. So the probability for that is pi raised to the power K. And this is then the same thing as the expected value of pi raised to the power Z. So this is the probability generating function. So it means that pi solves pi equals j of pi. So that is how you derive the probability of a minor outbreak. How about the final fraction infected? And let me stress that we're conditioning on in case of a major outbreak. Then you should think like this. Pick a random individual . Then, well, let's call that individual I. Consider her susceptibility set. So what is that? Well, here is my individual I. And the first generation of this susceptibility set are those, so maybe I am I. My susceptibility, the first generation of my susceptibility set are those individuals that would infect me directly if they get infected. So you draw the arrows going into you rather than going out to you. And then the next generation are those individuals who would infect the first generation in my susceptibility set. So maybe there are two people that would infect this guy, and no one who would infect that guy, and maybe one person would infect this guy. So that is the second generation. So the generation one, those who would infect me. Generation two, those who would infect generation two, generation one, and so on. The big difference now is that, consider me, what is my, if you call it what is my ingoing degree distribution? Well, this arrow here is completely independent of this arrow here, which in turn is independent of this arrow here, because these are potential transmissions, but from different individuals. Contrary to when you consider the index case and look at who would he or she infect, because here there is dependence. If my random infectious period is random, then these three arrows, whether they are there or not, are not independent events. But here they are, which means that my susceptibility set is approximate. I'm doing this a little bit sloppy. It's approximately branching process, but it's very connected to the Erdos-Reni network because of these independence. So maybe I should stress due to independence in degree. And then I said we are assuming that there is a major outbreak. Suppose there is a major outbreak. Then this individual I will get infected if and only if her susceptibility set is infinite. Why is this? Well, I don't know. I don't know the details, but I know that it's the probability that there are two infinite components in a random graph, infinite size components in a random graphs is zero. So if my susceptibility set is infinite and there is a major outbreak starting from the index case, then these two sets must coincide. So then it means that 1 minus tau, it is the probability for I not to get infected. Why is this? Well, if the fraction tau is the fraction getting infected and you pick a random individual, the probability that the individual is not infected is 1 minus tau, since you picked it uniformly in the whole community. And the probability that our index case does not get infected, that is the probability that the susceptibility set is finite. Which is the probability that this the branching process of in degrees goes extinct. By the way, I forgot to say here that this, since there is an arrow from each individual independently, the number of ingoing arrows is binomial with fixed probabilities. Yeah, so probability for yeah, so this corresponds to the in degree being Poisson R0, because we have this independence. So there is no dependence, and then we get my in degrees Poisson. So this is the probability of the branching process of in degrees going extinct when the degree distribution or the offspring distribution is Poisson lambda. And let's write what this is. So this is then, as before, we sum over k, and it is 1 minus 2 raised to the power k times Poisson lambda, so then R0 raised to the power k divided by k factorial times e to the minus R0. Sorry, it should be R0 here. And this is the same thing. If you rewrite this, you get this equal to e to the minus R0 tau. So you end up with an equation 1 minus tau is equal to e to the minus R0 tau. So the final size is the positive solution to this equation. So this ends what I plan to do handwritten. I will show some simulations illustrating these results now, but before I switch off my iPad, does anyone want to ask any questions about this?
Yes, Tom, I have a question. So this independence of your susceptibility set, this process, this looks sort of heuristically should be true very generally. So do we know that for more complicated process? So there are certain processes for which you can do the whole thing you did rigorous, where you can prove the differential equation and everything. So, but maybe there are situations where the process is so complicated you can't really do the differential equation, but you could still prove that this is correct. So do we know something about that? If you have some really complicated process you can't follow, but heuristically it should become easier at the end. But maybe then we can't really prove it. So that's my question.
Yeah, so I wouldn't dare saying when this type of reasoning applies, but in general, very frequently you can model the beginning of an epidemic by a suitable branching process, exactly what the suitable branching process is, but then it is sort of a forward branching process. And you have to define it. Sometimes you have to define a multi-type branching process, and otherwise it's clumps. So maybe in a household epidemic, the unit is not the individual, but it is the households. And you have different types of household sizes. But anyway, if you study the beginning, then you look at this forward process. Whereas if you're interested in the final size, you rather look at this susceptibility set, or some people call it a backward branching process. So it is how to so you pick an individual at random, and then the question is the group that would infect this individual, is that group infinite? Then you're likely to get infected, whereas if it is finite, you're unlikely to get, or with probability 0 in the limit, that you will get infected. I don't know if this answers the question, but maybe at least it relates to your question.
That was the heuristic I was saying I got from you. My question is, I don't know if you do this on a household model on top of a configuration model with deleting of batches when your parents are infected, make it complicated enough that you cannot prove the differential equation anymore. But maybe this would still be true, heuristically certainly, but is there sort of some way to prove this without just proving any, you see what I'm saying? There may be situations where you can't prove everything, but maybe sometimes we can't really prove everything, but we could still prove this. So have you encountered an example where you wrote a paper, you could prove the final size, but you couldn't prove the beginning size, or you couldn't?
No, that's a good question. You're right that, in fact, it's easy. If this particular example is the final size is easier because you have this independence, whereas in the beginning you don't have independence, so it's harder. You're right. I don't, at least not on top of my mind, I can come up with an example when you can compute the final size but not the initial phase. That would be very interesting. Yeah, so the answer is I don't know, and also that it's an interesting question to see if there are such situations.
So when you come, maybe we can start a little research group on that.
Yes, so we can discuss this when I come to Berkeley, hopefully. Okay, let me then go over to my slides. So I would actually log out of this thing. How do I do that? So now I only am on the laptop.
It's too small, it grows. If it's too big, it shrinks. Right?
Now I will share screen. And now so can you see the slides now?
Yes, we see them. Thank you.
Very good. So now, as I said, I will not go into any details of proofs, but more do a bit of heuristic and more of an overview. And I must admit that, okay, what I said last time, there was none of my own results, but today I'm sort of focusing on things where I have been working. Not all results are my own, but there is more about who has done what in the actual papers. So first, some simulations from the standard SIR illustrating the results I proved earlier. Then I will talk about my most recent result, which I find rather interesting, and it's called optimal prevention. So it has nothing to do with networks, and in fact, it's the deterministic model. But then I will go to epidemics with networks, and I will start off by having fixed networks, and then I will talk about networks that vary over time as an effect of the actual outbreak. I will try to motivate why this can be the case in reality as well. And then I will come back to this optimal prevention thing. So please interrupt me if there are some things that is unclear. So here's a very, very short recapture of this Markovian, in particular the Markovian SIR epidemic model. So it's an SIR model. Recall that we start with one infected, the rest being susceptible, and we have a fixed community of size n. Each infectious individual has infectious contacts at rate beta, and each time you pick a uniformly chosen individual. If this individual happens to be susceptible, that person gets infected and other contacts have no effect. And if it's the Markovian version of the model, each infectious individual recovers at rate gamma. So the model parameters are beta and gamma, and we have the population size. And R naught is beta over gamma, which is the beta times the average duration of the infectious period. I told you on Tuesday, or actually now also, that as n tends to infinity, the final fraction getting infected converges to a 2-point distribution. So there are some minor outbreaks where a fraction tending to 0 gets infected, or in the supercritical case, the final fraction getting infected solves this equation, which I just finished on my iPad. We will see an illustration of this. My other result, or one of the other results, a fraction of positive infected, then the actual epidemic process converges in probability to an ODE system which looks like this. This is probably the most well-known of all epidemic models, so I would call it the Deterministic SIR model. So the fraction of susceptible decreases at rate beta times the rate at which infectious and susceptibles meet. And when this happens, they go to being infectious. So there's a plus sign here, but also infectious individuals recover at rate gamma, and then they go to the recovered state. I will come back to this equation in the prevention thing as well. So maybe you can have this set of differential equation in mind. So let me first illustrate this thing, that the final fraction getting infected converges to a 2-point distribution, 0 and the positive number. However, the positive number is only available in the supercritical case. So what I've done on the next slide is that I have simulated this epidemic in a population of 1,000 individuals, and I've simulated 10,000 such simulations, and the only quantity I have stored in each simulation is how many people got infected. So maybe my first simulation resulted in 601 people getting infected. Sorry, and the third one, 39 people got infected. So I store these 10,000 final sizes and I plot a histogram of it. And here is how the histogram looks. The first histogram is when R naught is 0.8. I chose this number rather arbitrarily, but the important thing is that it is smaller than 1. So then we see that all outbreaks are small. When I do the same thing with R naught equal to 1.5, we still have some small outbreaks, but now we also have some big outbreaks, and they are not scattered all over, they are concentrated around 600. If I would have, we see here's the population size 1,000. If I would have done the same thing in a population of 10,000 individuals, this mountain would have been much more peaked. And it seems like the peak is slightly below 600 individuals. And this agrees very well with this equation. So if you solve this equation, when R naught is equal to 1.5, then you get that a fraction around 58.3% will get infected. So this seems to agree well with the peak of this mountain. And of course, we have this normal distribution around it, which I haven't proven, but which can be proven as well. So that was an illustration of the final size having a 2-point distribution. Minor outbreaks and major outbreaks, and the major outbreaks are located around the solution to that equation. And now we go to the, sorry, yes?
What would it be if you plug in the R naught of BA.5?
Sorry?
If you use the current R naught of our Omicron of 18, how would this look?
18.
Yes, that's BA5, right?
Oh, that's very well. Yeah, I will show it. There is a figure of that as well. Before I show that figure, here is a simulation of one epidemic, but I picked a typical one over time. So here the x-axis is the epidemic process over time. And what am I plotting? I'm plotting the fraction of infectives. So what fraction in the community are currently carrying the virus for the standard SIR model? And I start with 5% being infectious. And I do this when n is equal to 100 individuals, and we see that it's quite random. And here is this flat, this smooth curve, that is the deterministic SIR model. And when I do it with 1,000 individuals, we see the fluctuations are still random, but we're approaching the deterministic one. And when you have 10,000 individuals, we see that the stochastic fractions are very close to the deterministic model. I think here is the graph that you asked. Here is the final size as a function of R0. What I illustrated before, I said if you solve, I've solved this numerically on a grid there. So for 1.5, we go up here and we go horizontally to end slightly below 0.6. And when R0 is 3, I should have drawn a horizontal line here at 1, I realized. But at 3, we are quite close to 100% getting affected. I think it's maybe 98% getting affected or so. Of course, this assumes that we have a homogeneous community. Don't forget that. So if there are some individuals that are much less susceptible and some that are more susceptible, there is a small difference to this. But still, a big fraction will get infected when you have large R0, unless there is immunity in the community, of course. And there are loads of extensions for epidemic models, and there are a lot of there are a lot of solved problems for these extensions, but there are also a lot of open problems. And what are some typical extensions? Well, one is that you divide individuals into different types. Could be due to age groups, due to prior history of the disease, vaccinated and unvaccinated, and whatnot. Well, here comes including vaccination. You can also include other preventive measures. Of course, an important thing is to not to neglect that we have social structures in the community. And the most common such models are network epidemics, which I will talk more about, and household epidemics, which I will not talk more about. Then you can introduce a latent period. You can introduce waning of immunity. After some time in the recovered state, you go back to being susceptible. You can, if you look, of course, this is mainly important if you look at longer time durations. You can have dynamic populations, so people die and you are born. That's also maybe more interesting if you look at long time perspectives, but also complicated and having people move on. Effects of preventive measures, maybe that was up here. And of course, a very important thing is that the more complicated model you have, or maybe you can say the more realistic model you have, the more complicated is it to infer all the parameters of your model. So there's a trade-off. Putting more realism seems good, but on the other hand, you have to quantify more parameters, and that's the more parameters you have, the more risky that is. And then one slide, also none of my results, but just how do you include vaccination in your model? You do it as follows. Suppose that you vaccinate a fraction V before the disease comes. If it happens during the disease, you have to do a bit more complicated. But suppose that you vaccinate, you have a vaccine, you know the seasonal influenza is soon coming, so you give vaccines to some fraction V, and let's for simplicity assume that your vaccine acts perfectly, so the vaccinated people have 100% immunity. then in this standard SIR model, you get a new reproduction number, and this is related to the old one as follows. I mean, it's quite clear that suppose R0 is 5. If you vaccinate 40% of the community, you would no longer infect on average 5 people, but you would on average infect 3 people, because of the 5 people that you would have infected, on average, 40% of them are now immune. So 40% out of 5, that's 2 people, so you would only infect 3 people. And if you want your new reproduction number to be smaller than 1, meaning that after vaccination you are subcritical, this is very easy to solve this equation. That is equivalent to saying that my vaccinated fraction must exceed this quantity. I think this equation here is probably the most important equation of all in epidemic modeling. And it is used extensively by public health agencies for, let's say, childhood diseases. So if they know what R0 is, and you have a good vaccine, as for instance with measles and mumps and rubella and whatnot, then this suggests how many in each age group you have to vaccinate to maintain herd immunity, so to avoid big outbreaks. So this quantity here is called the critical vaccination coverage. And if you vaccinate more, you reach what's called herd immunity.
Tom, I have a question.
Yes.
So this seems it should just be super general if you really would vaccinate random people. Okay, so I mean, maybe different if you vaccinate the super spreaders more than the others. But if you would just vaccinate random people, can't I just think it as it's the same as if you would just reduce your susceptible population by a certain amount?
Yes, you're like always, you're a few slides ahead of my presentation.
Sorry. Okay.
You're correct, but I will show an illustration when, if you vaccinate uniformly, even in a more complicated situation, this relation holds. So that you're completely correct. But so I will comment on that later on. And if you don't vaccinate, so if you vaccinate too few, so maybe the critical vaccination coverage, well, for measles, it is probably, measles has R0 equal to typically like something like 15. So then you would have to vaccinate, I think 1 minus 1 over 15, I think that's about 93%. So suppose that you only manage to vaccinate 50%. Can you model what will happen? The answer is yes. So you would still be super critical, and you can compute the final size exactly like we did before. But this will be only among the unvaccinated, of course, because the vaccinated group, they're completely immune. And you solve that by doing exactly as we did before, but not for R0, but for RV. So then you get what fraction among the unvaccinated get infected, just like before. That was my short sort of illustration and also including vaccination. So now I will talk about epidemics, but before, networks. But before I do, I take the liberty to also talk about the new recent result of myself. So it is a deterministic model, and I'm a probabilist or applied probabilist myself. So this is a little bit outside my comfort zone, perhaps, but anyway. So we're considering an SIR epidemic, but now we include intervention. And suppose that there is no vaccine, and we don't foresee any vaccine to arrive shortly, within the next year or two. But what we can do is we can, this is a misprint, it should say pharmaceutical intervention. So define an arbitrary prevention strategy, P, and what is P? Well, it is a function of time, And the interpretation of small p of t is that we have reduced the overall contact rate by a fraction p of t. So if p of t one day is 50%, it means that rather than having infectious rate beta, people have half of beta infection rate. But this p of t, we can, maybe we are the public health agency or we're God or something like that. So we can sort of choose this. There are a lot of different preventive strategies. And the question is, what is a good prevention strategy? Anyway, and this is a function of time. So for that, I have this capital P as index here because it will depend on the whole prevention strategy. And it is exactly as the deterministic model, except that this we reduce the contact rate by this fraction P of t. So this is the remaining amount of contacts. So that's the only thing. And at least numerically, we can solve this up to infinity, and then we will get what would be called the final size. And let's call that Z of P or something else. Then there is a cost to a prevention strategy. Of course, maybe we're not willing to have a complete lockdown for half a year. So we assign a cost to it. And here we have assumed that we have a linear cost. Maybe that's not realistic. Maybe probably the true cost, whatever that is it's more to reduce the contact rate is probably cheapest when we start at the no preventions, but when we have sort of reduced our preventions for quite a bit, the cost is probably higher. But let's forget about that and let's assume that we have a linear cost function. Then the question we have addressed is the following. Suppose that someone has said we cannot have a cost of the prevention exceeding some number C. And suppose we want to minimize the total fraction getting infected or the final size. Then which prevention strategy should we use? This is not the only optimal criteria. Another one is to, rather than minimizing the final size, you might want to minimize the maximal number of infections. If you remember, that would correspond proportionally to not having at any point in time the hospitals overloaded. So that's a different optimization criteria which other people have studied, but we studied the final size, and I guess you can, that would probably correspond to the number, the total number needing hospital care. It would be proportional to that.
Or the total number of deaths, probably.
Yeah, well, maybe the total number of deaths, but then you can say, well, if the hospitals get too many people there, then maybe the quality of the hospital care is deteriorates, and then maybe more people will die among those getting infected. So maybe it's better to say the number of people requiring hospital care. So here, this is the number of infectives in the uncontrolled model, the standard SIR model. So it goes up. Here the number of, this is a peak, the incidence peak, and then it goes down. And here are a few different suggestions for preventive measures. So preventive measure 1 says that have a complete lockdown right away, and then maybe this is 1 month. And then after 1 month, we go back to complete normality. Prevention strategy C3 says, let's wait for 2 months and then we have a complete lockdown. Prevention strategy, this 4 says, have a 50% lockdown for 2 months in this period of time. Prevention strategy 5 says, let's increase the lockdown over time, sort of sort of mimicking the uncontrolled incidence and then have it drop, or a 25% lockdown for 4 months, or you can go up and down, whatever. So there's a wide range of possible prevention strategies. And the question is, which of these or any other strategy is the best one if we want to minimize the total fraction getting infected? And remember that well, here is one having a complete lockdown and then a gradual decay as well. And at least, as you see, this is handwritten, but my aim was to have all of these different prevention having the same integral, which corresponds to having the same overall cost. Was there someone wanting to say something?
But there are certain things which are counterintuitive here, right? So if I would just put all my resources in the beginning, you might say I kill the infection, but in your continuous model, there's sort of some tiny epsilon left.
Yes, that's a good comment. That's a good comment. So this is a deterministic. So this is a deterministic model, and it can never go extinct. Then you might say, well, in reality, we have a stochastic model and a finite population. So then if you put in a massive lockdown in the beginning, maybe you will manage to have this the epidemic going extinct, and that would of course be very successful. However, then you would require that there was no further immigration of infectives. So I think that strategy might work in islands like maybe New Zealand, but if for one country or one state in US or one country in Europe, I think it's impossible to believe that there will be no further influx of infectives.
So this would,
but you're right.
Indicate that. So in your continuous model, this would indicate if I put all my resources in the beginning, all I'm doing is, okay, so I will start with epsilon people infected, I reduce it to epsilon over 500, and then your infection will just run its course and you get exactly the same as before, and you wasted all your resources. That's
correct. The only positive thing you have done then is that you have delayed the epidemic, and in some situations that might be good, but the final size will be the same. So that's completely correct. Anyway, think more about this. If you get bored from the other things I will say, I will talk about the optimal solution at the end of the presentation. I think I will skip the now forget about this prevention. I will return to it at the end of the presentation very briefly, but now let's talk about networks. Before I say networks, there are a lot of different heterogeneities. You can think of individual heterogeneities, and individuals might differ in terms of susceptibility, infectivity, or the overall contact rate. And also, whom they contact and the overall contact rate. So then you say, well, if that's true, why do I even talk about the standard SIR model? Well, I think that this simplification that I talked about still makes sense for some diseases. It's a fairly good approximation for some diseases, in particular for diseases that have high infectivity. So the more infectious a disease is, I think the less problematic it is to make these simplifications. Whereas for diseases that are less infectious, then it's more important to take the different heterogeneities into account. And the least infectious type of this infectious disease you have is sexually transmitted diseases, but also some others. So then heterogeneities really matter. If you're interested in individual heterogeneities, you do what's called a multi-type epidemic, which is related to a multi-type branching process. I will skip that. And if you have households, then as I said earlier, the trick then is not to consider individuals as your unit, but to consider the household as your unit. Then you have different types of individual, different household sizes, but also households of the same size. They have a random infectivity because in some household of size 4, everyone gets infected, so they are doing more infections outside, whereas another household with 4 people, perhaps only 1 person gets infected, so they will infect fewer outside their household. So also the infectivity is more random in that situation. But now let's go to epidemics for the rest of this presentation, except the final slide will be a solution to this optimal prevention. Everyone knows what the network is. Here it is used for describing the social structure in the community. So for that reason, it makes sense to consider networks that are undirected, because usually if I'm a friend of you, you are a friend of me. So most of these networks are undirected. So what is a good random network? Well, of course, that depends on what particular disease you're interested in, and in particular how it spreads. But also, in some situations, you might know a bit about the networks, and in other situations, you might not. Things you might know about is the degree distribution, how many friends people have on average or in distribution. And then there's another thing called clustering coefficient, because in most social networks, if you pick 2 individuals at random, it's very unlikely that they are connected to each other. But if you pick 2 friends of an individual, the probability that these 2 friends also know each other is much higher than 2 random individuals. So that is captured in this clustering coefficient. And then there's degree correlation. So individuals with high degree, do they tend to mix with other individuals of high degree? If yes, you have a positive degree correlation. If individuals with high degree rather tend to socialize with individuals with low degree, then you have negative degree correlation. So I think there are features of both of these situations, but probably it is more positive degree correlation in social networks, I think. But most of the things in your network you don't know. For instance, in sexual networks, fortunately, no one knows how the sexual network in a community looks like. So then you might use a random model, but you want it to satisfy whatever you know about the network. But other than that, you treat it as random. I will mainly talk about situation when so I will not talk more today when there is positive clustering, nor any specific degree correlations. I will focus on configuration model type networks. And then now, for the moment, I will talk about the simplest epidemic model taking place on such a social network, and that is where you infect each of your friends independently with probability P. So that sort of resembles the Reed-Frost model. So if you want, you can think of that you have a constant infectious period during which you infect each friend independently. But anyway, you have a social network, which is random, and on that network, if I get infected, I infect each of my susceptible friends with probability P, and then I recover. The way to model that on the graph is that you thin each edge, you remove it with probability 1 minus P, then the remaining edges, you can think of them as potential spreading. So if this is your social network, you remove each of these edges with probability 1 minus P. So maybe I remove these 4 edges and I kept these 3. So then this is the thinned network. And then you pick a random individual who is your index case, So if it is this individual, the result is that not only this person gets infected, but also that one and that one. Whereas these other people don't get infected. So that's how you would model it stochastically. But for now, let's focus on the configuration, a network epidemic for having an arbitrary degree distribution, which I call, well, this is the degree distribution. And we model the network by a configuration model. My guess is that most people know the configuration model, so I will not describe it here. And as I said, the epidemic model says that you infect each susceptible friend with probability P, and you do this independently. And let's suppose that we have one randomly selected index case. Then what is, for this model, what is the basic reproduction number? This slide, I think I've presented this particular slide over 100 presentations. But it's harder when I don't see the audience in front of me, so I will, but when I do it in live, I will always get people to guess what I've written down here. So if on average, suppose you have a Poisson distribution or some other distribution, and suppose the mean is 5, and suppose you infect each one with probability P, let's say the P is 0.5, how many on average do you infect? Well, the first guess that comes to mind is, of course, this on average, and you infect each one with probability 0.5, you will guess 2.5. So that's the first guess that comes into mind. Unfortunately, that's wrong. So why is this wrong? Well, suppose I have degree 5. If I get infected, it means that I have been infected by one of my friends. So then I only have 4 friends left. So then the mean reproduction number should be P times the expected degree subtracted by 1. However, that is also wrong. So why is this wrong? This can be explained by the following picture. Here are sort of 6 typical individuals. This guy has 2 friends, 1 friend, 5 friends, 0 friends. So who would you bet on getting infected in the beginning of an outbreak? I think everyone would bet on this guy. No one would bet on this guy, because if you have no friends, you will not get infected. So if this here sort of mimics the average degree distribution in the community, it does not mimic the degree distribution among those getting infected in the beginning. They will have a different degree distribution. They will have a degree distribution which is the size biased degree distribution. So it is K times PK, proportional to that. And the reproduction number is this mean degree of the size biased degree distribution, subtracted by 1 since you were infected by 1 person, and multiplied by the probability that you infect each of them. In terms of the original degree distribution, this has the following expression where V of D is the variance of the degree distribution. So the basic reproduction number does not only depend on the transmission probability and the mean degree, but it also depends on the tail of the degree distribution. And that is unfortunately, unfortunate because nearly all empirical networks that have been analyzed tend to have a heavy tail degree distribution, which means that this factor here is substantial. So even when the transmission probability is small and the mean degree is small, you can still be supercritical from the fact that the variance of the degree distribution is large. Yes, and you can compute these things, the probability of a major outbreak, and also the size. I will not go into details, but you can do that sort of in a similar way to what I described earlier, but slightly more complicated, not that much more complicated. So now we go to vaccination, and now I will illustrate what Christian mentioned earlier, I think. So how about if we vaccinate in this model? Well, then the question is, who do we vaccinate? Let's start with the simplest case. If we vaccinate randomly chosen individuals, then the new reproduction number is, as Christian already realized, it is the original one multiplied by 1 minus the fraction being vaccinated. So this means that you need to vaccinate the same type of expression. Of course, R0 is before, but still, if you know what R0 is, you have to vaccinate. And if you vaccinate such that the new reproduction number is more than 1, then you avoid future outbreaks. The critical vaccination coverage is as before. However, this is problematic because if we have a very large R0, it means we have to vaccinate the huge fraction in the community, and maybe this is not possible. I mean, if the variance is large, it would mean that if we vaccinate uniformly, we would have to vaccinate close to everyone, and maybe that's not possible for some vaccines. Maybe the vaccine doesn't work perfectly, and then even if you vaccinate 100%, you might not do it well enough. So can we do better than selecting vaccinees at random? Then if you think a little bit about it, I think that was also mentioned recently. You should, of course, vaccinate social people or the super spreaders. The problem is, of course, that most of the time you don't know who are you don't know the social network. There is no list of who has most sexual contacts or who has most social contacts. But maybe you can try to get that somehow. But if not, here is an academic example of a better vaccination strategies, and it goes as follows. It's called acquaintance vaccination. So you pick individuals at random, but rather than vaccinating them, you vaccinate one of these randomly selected individuals' friends. So the friends of the randomly selected individuals. By doing this, you will vaccinate individuals having this size biased degree distribution rather than original one. And this is much more efficient. Of course, it wouldn't be realistic, but one thing you could do if it is sexually transmitted diseases, maybe you say, here is your vaccine, but we would also like to vaccinate your partner. So then you would vaccinate some randomly chosen individuals, but also their partners. And typically, partners are more sexually active. It follows from the sad fact that your friends have more friends than you do. So that would be much more efficient, which is illustrated in this figure. Here we have the critical vaccination coverage for some situation when the degree distribution is Poisson. Here is acquaintance vaccination, and here's a uniform vaccination. So not a huge difference. But then when we picked a heavy tail degree distribution, I forgot exactly which one it was because this is 14-year-old, I think. Then the acquaintance vaccination, it sufficed to vaccinate 50%. Whereas we would have done uniform vaccination, I think we would have needed to vaccinate close to 77%. So that illustrates that acquaintance vaccination would be much better. So that was what I plan to say about epidemics on a fixed networks. And then I will move on to the more complicated situation of what I call adaptive networks. But before I do that, is there any question on these fixed networks?
I have a question, Tom. which
Yes.
so if instead of vaccinating, I would just say, okay, let the people get sick and wait for herd immunity. And now, since the infection tends to do exactly what you're trying with your sexual contact, it will infect my friends. So the natural immunity, the natural herd immunity should therefore work sort of better on power law graphs than on non-power law graphs. Is that true?
Yeah, I missed a little bit what you said, but I think I still got what you aim for. So if you have a heavy tail degree distribution, the effect of that, let's say, if you fix the mean of a degree distribution and then you play around with the variance, then the bigger variance, the bigger R naught will be. That is always true. However, it is not true that the final fraction getting infected increases with the variance. Typically, it's the opposite. That well, that depends on the overall transmission rate. Let's say, but if you have a very heavy tail degree distribution, then you can have a situation where you have a very large R naught, but if you just let the epidemic run, a rather small fraction get infected, and it's the super spreaders that get infected and not so many more, let's say. I don't know if that is what... So it is not... R naught is monotone in the variance if you fix the mean, but the final size is not monotone in the variance if you fix the mean. Does that connect to your question? I didn't hear, so I assume I will continue.
This was not quite my question, but I think it's related to it. I was asking about herd immunity, which seems to be similar because, again, if you have large variance, then you might naturally infect the super spreaders first. And once you have infected the super spreaders, you might already have herd immunity, whereas in a homogeneous one, you don't have it yet.
Yes, that is true. In fact, that is, I don't have that in my slides here, but well, at least the paper that has been cited the most by far of all papers I've written was a paper I wrote in Science June 2020, so right after or during the early stage of the pandemic. And there we showed that if we acknowledge that a community is heterogeneous, then the herd immunity level is actually smaller than if we treat it as a sort of homogeneous community. I think that I cannot talk everything today. Maybe we can discuss this more. So I will continue now. That paper that I talked about was published in Science. I guess that's also partly why it was cited quite frequently. So now let me talk about networks which change over time. So if you have no preventive measures, depending on what model you have, hopefully you can try to compute what fraction will get infected as a function of all your model parameters. So theta is the vector of your parameters. However, at least if you have severe diseases, then even if the society does not invoke any preventive measures, individuals will take precautions anyway. They might isolate themselves, they might distance themselves from infected people, they might wash their hands more, or if it's a sexually transmitted disease, they might start using condom or whatever. And this, the work here was initiated before COVID-19, so we were mainly inspired by Ebola, where it was clear that people changed behavior because they got frightened of the Ebola outbreak. And this was manifested in the sense that there were no, at least in the beginning, there were no sort of public health measures, but still the final size was much smaller than anticipated by the model. So adaptive dynamics is models where individuals change behavior as an effect of the epidemic process. And I will focus on the situation where we have a network. So you have some friends, but if some of your friends get infected, then you might stop seeing them. So what is the effect of social distancing from neighbors or friends? Neighboring is in the graph sense, but maybe in the social sense, it would mean friends. So this we have done in a series of papers. And these happen in continuous time. And as before, we're considering a large population. And I would assume that the social network is described by the configuration model. And before the epidemic, this network is static. And on that, we have a transmission model. You infect at rate lambda and you recover at rate gamma. I'm sorry that this is no longer beta. It used to be beta in the homogeneous case, but here for some reason we have called it lambda. So then the social distancing works as follows. So if you are susceptible and you have some infectious neighbors, then you rewire your edge to that individual at a rate which is called omega times alpha, and you drop your edge individual at rate omega times 1 minus alpha. So omega is the rate at which you do something, and alpha is the probability that something is that you connect to a new individual, randomly chosen, and 1 minus alpha is the probability that you simply drop this edge.
Tom, can you be clear? Because I thought you would do something and this looks different. So if I have 50 friends and,
yes.
and I'm susceptible and one is infected, then I rewire all my 50 friends or only
no. You only rewire from those that are infectious.
Okay.
So you can sort of, maybe a better thing is to think of omega is the rate at which you discover that your friend is infectious. And then you take one of two actions. One is to drop that connection, and the other action is to rewire to a new friend who hopefully is susceptible. So you only do this to infectious individuals. So the model parameters are lambda, that's a transmission rate to each friend. So this is the individual transmission rate. So if you have 5 friends, you infect each of them at rate lambda. Gamma is the recovery rate. Omega is the rate at which you let's say you discover that your friend is infectious and you take some action. And alpha is the probability that your action is to rewire to a new friend. Alpha you drop, and D is your degree distribution, which has mean mu. So no latent period, and we have constant infectivity, Markov assumption, blah, blah, blah. The special case where there is no rewiring, well, then the model is no rewiring. So that is well understood. It has been analyzed by many models. That's just what I talked about earlier, the network model without any action. But when omega is positive, we can consider the situation that alpha is equal to 0 and alpha is positive. Alpha equal to 0 means that you only drop edges. And that turns out to be at least not as hard to the situation when you also rewire. And we have had quite complicating factor is that the probability to get infected from a neighbor changes over the course of the epidemic. an obvious result is, suppose that each individual has their own omega. So this model, everyone has the same omega, but suppose each individual has their own omega. So omega is the rate at which I take an action when, take an action when a friend of mine is infectious. Then it is clear that the quicker I do this, the more likely is it that I escape being infected. So the probability to get infected decreases with this rate omega. That is clear. However, so I'm mixing slightly here, but up in the model, everyone has the same omega, but still, sort of from an individual perspective, it makes sense to have a big omega. And this is how it looks. So if this is an infectious individual and this is me, I'm susceptible, then I seem to have 3 friends. One is susceptible, I do nothing. Here's an infectious person, so I take action at rate omega to that guy, I take action to that guy at rate omega. And the action could be that I either drop this edge or else that I rewire it, and then I would pick a random individual in the community. So that's the model. I realized that. So can someone tell me how much more time do I have? I don't have a full working clock. I think I don't have that much more time. How much more time?
Official 4 minutes, but maybe we can a little bit more.
4 minutes.
But you can get a little more. That's it.
You can get a little bit more, Centane. That's good.
Okay, but I think I'm approaching the end there, but anyway. The beginning of this outbreak is possible to analyze. And then, in fact, it doesn't matter if you drop or rewire, because even if you rewire, it's very unlikely that you will rewire to someone who's not susceptible. So dropping and rewiring will be the same thing. And the basic reproduction number is similar to before. So it is the expected value, this size, bias, degree distribution times the probability that you infect the neighbor. And that is now, this is the rate at which you infect, this is the rate at which your friend, at you recover, and this is the rate at which your friend drops or rewires away from you. So if you look at this expression, clearly R0 increases with the infection rate and decreases with the rate of recovery and decreases with the rate of taking action or rewiring and dropping. And this is exactly what you would expect. And we also see that if omega is big enough, whatever this is, if omega is big enough, this quantity is below 1. So if you rewire or drop quick enough, you will be subcritical. The dropping model is easier to analyze, and there sort of a big, nice observation is that rather than thinking of me rewiring away from someone, you can think of it that it's that person who informs you that they are infectious. And these individuals inform their friends independently at rate omega. That's an identical model, but then you can modify this model by saying that an infectious individual does not inform their friends independently, but instead they inform each of their friends at the same time, but with the same rate. Then you get a slightly different model, but it turns out that it's not such a big difference. And this model is much easier to analyze because, in fact, this modified model is identical to a model without rewiring, but having a bigger rate of recovery. Probably this was a bit complicated, but anyway, so this can be solved quite easy. The more complicated situation is when you also rewire. So what I said before, the chance results, the result follows. There are two interesting quantities, I think. One is what is the final size as a function of the rewiring rate. So you would expect that the more you rewire, the fewer people will get infected. But this theorem proves that is not always the case. So there are degree distributions and parameter sets such that you will have a bigger outbreak when you rewire as compared to when you don't do anything. So you will have a bigger outbreak when people take preventive measures. The heuristic explanation is that consider an individual with very high degree, even if it rewires, it will most likely, even if it rewires with a small rate, it will most likely get infected. And if it does, it might have rewired to individuals with a lower degree. And yeah, I'll skip that. So now let's consider the final size as a function of the infection rate. Then we looked only at we had a lot of problems proving anything. So we looked at only Erdős-Rényi networks with mean mu. So if we fix the mean of the Erdős-Rényi network, assuming it's bigger than 1, we fix the recovery rate, we fix the rewiring rate, and we fix the rewiring probability. Then we set the critical lambda looks as follows. This is exactly the lambda value. It's the critical lambda value such that the basic reproduction number equals 0, and equals 1, and when the basic reproduction equals 1, there will be no big outbreak. But then we have a theorem that if 2 criteria are fulfilled, then the final size, if you are just above this critical value, will not be 0, but it will be strictly away from 0. I will now end by illustrating these 2 results. So here is the final size as a function of the rewiring probability for some specific choice of degree distribution. We see when we don't rewire, I think the population size was 5,000. When we don't rewire, we on average got 3,200 people getting infected. But then with rewiring, you see that there are even more people getting infected. This turned out to be also a case for some empirical networks that we looked at. We downloaded 12 networks, and a few of them actually had this feature that if we played around and rewired, we would get a bigger outbreak. The last illustration, which we proved most recently, is the final size as a function of the transmission rate for some specific choices in a population of 1,000. Here, if you remember, there was a criteria here. This criteria is fulfilled in the right figure, but this criteria is not fulfilled in the left figure. So in the right figure, we see that when lambda is small, we only have small outbreaks, but when lambda is above this critical value, we suddenly have some big outbreaks, but there are no outbreaks here. Well, there were 2 of them. When in the situation there was no discontinuity, we see that they follow this line. Okay. So that was this result about dynamic networks. 2 rather surprising results, that the final size is discontinuous in the infection rate, and that if rewire, you might even do worse than not rewiring. Finally, the result about the optimizing preventions. Which preventive strategy is the best? Given my criteria, the answer is that we should do nothing until the peak of the incidence, and then we should have a complete lockdown for as long as we can afford, and then we go back to normality. Elaborated this a little bit. So we also said, suppose we cannot have a complete lockdown. Suppose that we can have, let's say, a 50% lockdown at the most, or a 75% lockdown at the most. And the next slide, I think, is for the situation when we at most could have a 75% lockdown. Sorry, here is the result. Given a starting value, and suppose that we want to minimize the total incidence, I didn't introduce, but this is the final fraction getting infected among all piecewise continuous intervention strategies, with an overall cost not exceeding this constant C1, and with the maximum lockdown does not exceed some other constant, which in this numerical slide we chose to be 75%. Then the best intervention strategy says do nothing, and then do the maximal possible lockdown, and then go back to doing nothing. And here is a figure. So what is this? This is I of t. The black curve is without interventions. And then the blue curve is the optimal strategy if you want to minimize the total fraction getting infected. So then we should, because 75%, we should start slightly before the peak of the uncontrolled incidence. We go up to 75% until our money, until the cost has exceeded, and then we go down to 0. So we see the incidence will, of course, before intervention, it will behave just like no intervention. And then when we have 75% lockdown, it will suddenly drop and go down like this. So that is the best strategy. The red strategy is the best strategy if we want to minimize the maximum size any point in time. So this would be a strategy for making it pleasant or as least unpleasant as possible for the hospitals. So we would have sort of keep the incidence at the maximum level, and the best strategy for that has been proven by others, and it says you should start the lockdown slightly earlier, then gradually drop it. I think even if people are okay with wanting to minimize the optimal, the total number getting infected, I think very few people from public health agencies would be comfortable saying do nothing up until we more or less have the peak incidence. So let's say, as a toy example, suppose you present that this blue here is the best thing we can do. I think they would say, no, I don't trust you. I give you some more money so you can start your prevention early. So end it here, but start it earlier, maybe sometime a week earlier or something like that. What would then happen? So here is the original one, the best, and here is where they give you one more week of lockdown and do it before. The effect is that you will follow the red curve, but then when you stop, you will have a new big outbreak. And we see that this is the overall fraction getting infected. So the consequence of adding a week of prevention before the optimal solution is that you will get the big second wave. And if you look at the total fraction getting infected, you will hardly gain anything from having no prevention. So rather counterintuitive, by adding prevention early, worse.
It's not counter.
That was, sorry?
I find it very intuitive, because if you prevent too early, then you will freeze the epidemic when your effective is still high, and you just wait time. You can do as long as you want. You sort of, if you could do it perfectly, and then eventually you just start at the same place, where are effective is still high. If you start
Yes.
a week or later, are effective is smaller than 1, and now it's used. So that would
Yes,
be
you're completely correct. So it is not counterintuitive. Still, I think most people would find it counterintuitive. But so I think you're an exception, and I've given this presentation, I've given these slides, presented these last slides a few times, and nearly always people are very surprised about this. Anyway, I'm done. If there are no regarding this or anything else.
Okay, thank you so much, Tom. So let's thank the speaker. So maybe some quick questions. We'll ask some questions, I guess. Yes.
Thanks for that talk. Is it possible to reason about R naught if you're not choosing the first individual randomly, but maybe like a influence maximization case where you choose the first person to maximize the spread?
So who is the index case has a big effect, at least if you consider network models or whatever. Who is the index case has a big effect on the probability of an outbreak. However, who is the index case has very little, or I would even say no effect on the basic reproduction number. So it does affect the probability of seeing an outbreak, but it does not affect sort of the asymptotic, if it does not affect, if it takes off, it doesn't matter who was the index case. So who is the index case has a big impact on if it takes off, but if it takes off, it no longer matters who was the index case, if I put it like that.
Thank you.
Anyone else?
Maybe I can ask a quick question. So what about this degree correlations? So
Yes.
I'm thinking that if you have hubs connected to hubs, then probably they form some kind of backbone early on. So can you comment briefly maybe on what would happen if you have positive correlation or negative correlation? How would it affect the process?
So I think this will depend on sort of the overall amount of on the overall infection rate, let's put it. So let's see now. If you have a highly infectious disease, then the only ones that will escape are individuals with low degree that connect to other individuals with low degree. So if you have a high infection rate, my guess is that the final size will be smaller if your degree correlation is positive. Whereas, well, I'm not 100% sure. Whereas if the overall transmission is not so high, then the only way to infect the people with low degree is if they tend to connect to other individuals of high degree. So that's star formation. If you have a star formation, then also individuals with low degree are likely to get infected. I don't know if that's well enough, but I think some stuff is known about the degree correlation. Of course, it depends on how you define it. There are many different models producing positive and negative degree correlation, but I think I didn't respond well enough, but some stuff is known about it, and it depends on sort of the overall transmission rate.
So is that rigorously known, or is that more simulations and physics kind of arguing?
Well, I have analyzed the model having I am Frank Ball. We sort of defined a model inspired by the configuration model, where we also had clustering, a parameter affecting the clustering and another parameter affecting the degree correlation. So for that particular model, we were able to show that how the degree correlation was affected the final size. But I don't remember all the details of that now.
Maybe you could add that reference to your slides before we post them.
Yes.
Okay, so thank you so much. So I guess that we can keep it as open problem maybe for the future. So thank you so much again. Let's thank Tom for one more time for excellent talk.
Thank you very much.
I guess we have no break. Resume at 11 minutes. Thank you so much.